Hello, my name is Mohamed Ali, and I'm here with my teammate Mehmet Akif. We will present our project for this course, Adaptive ANC for Hearables using IMM filters. The one-line story is on the right side of the slide. We built an app adaptive noise canceller that delivers 16 decibels of noise reduction across the changing environments. Runs in real time with C-port 56 microseconds per sample, and beats the best single fix filter by a factor of 2.7. We will show you how and why it works because reasons turn out to be more interesting than we first expected. Let me start with the core problem. Active noise cancellation uses an adaptive filter to learn the noise and playback anti-noise signal to filter that one critical knob, its adaptation speed. Look at the two plots on the left. The top one is slower filter in a quiet room. It's beautiful, stable, precise, low residual, but the moment environmental change at the 5-second mark, it lags. It takes seconds to recover. The bottom one is a fast filter. It recovers from the change almost instantly, but in the quiet stretch, it's restless. It's keep injecting its own noise. So we are stuck. Slow is good in quiet, bad at transition. Fast is the opposite. In real life, walking from a quiet office to into traffic, then wind, then a crowded cafe, changed within seconds. No single fixed setting is safe. Our goal, one controller that adapts its own speed online to whatever it hears. That's exactly what the IMMs gives us. Here's the system. It's a standard feed-forward ANC topology. A reference microphone picks up the noise. The noise also travels through the primary path. P of Z, it's error microphone. Our controller filters the reference through the secondary path. S of Z and drives the speaker to cancel the noise at the ear. The key equation is on the orange box. The residual E of key equals to D of key minus V transpose times the filtered reference. Now here's the insight that shaped the whole project. The residual is exactly the Kalman filter's innovation term. So casting ANC as a Kalman estimation problem isn't an approximation or analogy, it's exact. The observation model is linear in the filter weights, which, as we'll see in the two slides, means a plain Kalman filter is all we need. At the bottom, you can see the actual estimation primary and secondary paths impulse responses we used. So we pose the filter weights as the state of Kalman filter. The process model is on top of W at time k equals at W k minus 1 plus process noise q. It's a random walk. F is the identity. And let me say why a random walk. The ideal filter genuinely drifts as the room changes, but we have no parametric model of how it drifts. So maximum entropy, honest choice is to assume no preferred direction and put all of our model effort into the sigma q, which controls how fast we are willing to follow that drift. The single most important parameter here is sigma q, the process noise standard deviation. It is the adaptation speed. Small sigma q means slow and stable, large means fast and reactive. That's the exact trade-off from slide 2. Now look at the table. Our 4 mod spans sigma q 3 times 10 to the minus 9 for a quiet office, all the way up to the 10 to the minus 3 for Babel. That's 8 orders of magnitude. one bank of filter that covers everything from whisper quiet room to subway platform. The measurement model completes the Kalman setup. D of key equals the filter's reference transpose times the weight plus measurement noise V. The thing to notice on the left, the model is linear in W. The observation matrix H is just the filtered reference vector. Because it's linear, the standard Kalman update applies directly. There's simply no nonlinear to linearize, so we don't need to extended or unsent Kalman filters. They will add computation for zero benefits. As the green box says, the playing Kalman filter is exact here. The second per mode knob is sigma r squared. The measurement noise variance lower sigma r means the filter trusts each new measurements more, so it reacts faster. You can see the tightening. Across the table, 1.0 for quiet down to 0.01 for bevel. So each mode is just sigma q and sigma r pair. Four of them. Now how we combine them. This is the heart of the system. Interactive multiple model bank. We run 4 Kalman filters in parallel. One per mode, quiet, bevel, traffic, wind. Each with its own sigma q and sigma r. Follow the 4 steps on the right. Step 1. Mixing. Before each update, we blend the filters estimate together, weighted by their mode probabilities. Step 2. Kalman update. Each 4 filters run its own update and reports how surprised it was. It's innovation variance. Step 3. The Bayesian update. We update each mode probability based on how well it predicted latest residual over a window of 200 samples. Step 4. Combination. The output is the probability weight average of all 4 estimates. And critically, those mode probabilities are fed back into the mixing step every single sample. Keep that feedback loop in mind. The configuration is at the bottom. 64 tabs, 200 sample window, 4 modes. With that, I will hand over to Mehmet Akif for the experiments.
How do we test something built for changing environments with a deliberately hostile dynamic scenario? The timeline at the top shows it. 20 seconds, substitute 4 5-second segments, quiet, then traffic, then wind, then babble. And at every boundary, we physically swap the acoustic plant, so the filter is forced to reconverge 4 times. Below the timeline, you can see the actual signals. The mode condition noise source, the primary signal at the error mic, and the filtered reference. On the right are the methods we compare. 2 NLMS baselines, slow and fast. 3 single mode Kalman filters tuned for quiet, traffic, and winds, and finally our IMM-KF. We score everything on noise reduction in decibels and on-mode tracking accuracy. And to be fair, we average over 15 Monte Carlo runs, each with fresh random paths and noise. Here are the headline results. The top left chart is overall noise reduction over the 15 runs. Look at the baselines first. The NLMS filters get about 5 and 6.5 decibels. The single Kalman filters, even the best one, a KF Wind, top around 6 decibels. And notice KF Quiet collapses to just 2.6 on this dynamic scenario. A filter tuned for one environment is genuinely unsafe when the world changes. Now the IMM-KF. 16.06 decibels. That's 2.7 times the best single filter, and with a standard deviation of 1.8, it's also the most consistent. One honest caveat on that number, These are controlled synthetic blends. So a real device with a path estimation error and microphone noise would see somewhat less in absolute terms. But the part that matters, the relative 2.7 times margin over any fixed filter, is exactly what carries over the hardware. The bottom panel is per mode misalignment. How well the weights match the ideal filter. So, and you might ask, why is the Babel column for poor for everyone? Good question, and it's revealing. Babel is band limited noise, 200 to 3500 Hz. Out of the band, there is nothing to excite the filter, so the weight can't converge there, and that's true for every method, which is why the whole column saturates. But in band noise, reduction stays high. Misalignment and NR are not the same story, which is the perfect lead in to the next slide. So, why does the IMM win? Our first guess was the obvious one. It must be identifying the environment and switching to the right filter. We tested that and we were wrong. Look at the top. The full IMM gives 16 decibels, but when we turn mixing off, set the interaction matrix to the identity, so the filters run independently, performance collapses 1.5 decibels. The mixing step is essentially doing all the work. And here's the twist. The mode tracking accuracy is only 18%. The filter is wrong about which environment it's in most of the time, yet it still delivers 16 decibels. You can see it. In the quiet segment, it actually thinks it's in traffic. So this is not a classifier, which means that 18% figure isn't a failure at all. The foremost were never meant to be environment labels. They are a dictionary of adaptation speeds, and the combination step just blends them. We never have to pick the right one. What the IMM really is, as you can see in the bottom box, is a self-receding bank. The slow, accurate filters are kept alive by mixing in a little of the fast filter every sample. So, a sudden change in the IMM never has to fully reconverge. The mixing, not the classification, is the engine. That was the most surprising and honestly the most satisfying finding of the project. A good algorithm that can't run on the device is useless. So we ported the IMM to plain C and measured it. The numbers on the right are per sample latency for the IMM. In Python, it's about 495 microseconds, roughly 8 times too slow for real time. Our pure C scalar port brings that down to 56 microseconds and 8.8 times speed up, which sits comfortably under the 62.5 microseconds budget at 16 kilohertz. Real time factor 0.9. It fits. Now, an honest finding. We expected an optimized BLAS library to be even faster, but it was actually slower, 77 microseconds over our budget. The reason our matrices are tiny, 64 by 64, and that size, the library call and threading overhead dominates the actual arithmetic. Scalar C keeps everything in cache with no call overhead. So, for embedded ANC, plain scalar C is the right choice. A useful lesson for anyone building one of these small on hardware. And those numbers, 64 taps, a 200 sample window, aren't arbitrary either. They're the knee of the noise reduction versus latency curve from our parameter sweep. More taps buy a little more NR, but eat into exactly this real-time headroom. So 64 and 200 sit at the Pareto optimal points. Decibels are one thing, but does it actually sound better? To check without hardware, we built a virtual headphone. It models passive isolation in the high band, applies the ANC only in the low band where it belongs, and renders all the versions with one shared gain, so the loudness drop and you'd feel is preserved. The table compares methods perceptually. And here we're being deliberately honest. Yes, the IMM has the highest noise reduction, 16.5 decibels, and the best signal to noise gain. but it also has the highest musical noise. Those little warping artifacts. So, the metric says the best and the ear don't fully agree. A single number can hide the tension, which is exactly why we built a bench that lets you both measure and hear it. And the live demo, you can actually listen to the difference. So, to wrap things up, we have three takeaways. One, our IMM-KF delivers 16 decibels of noise reduction, 2.7 times the best fixed filter, and it gets there through Bayesian mixing, not classification. It tracks the true mode only 18% of the time, and it doesn't matter. Two, it's a real-time capable. Pure C, 56 microseconds per sample, inside the 16 kilohertz budget, and we learned that the simple scalar code beats the heavyweight library at this scale. 3. We evaluated it the way it's actually going to be used, through a virtual headphone with perceptual metrics. So, the trade-offs are both audible and measurable.
This is the live demo of our project, adaptive noise cancellation driven by IMM-Kalman. The app has two pages, Performance Lab, where we run the controller live and inspect the engineering metrics, and Music and Feel tab, where we listen to what ANC actually sounds like through a virtual headphones. So, first numbers, then experience. 16 decibel of noise reduction. That's the Monte Carlo headline from our reports. Let's look at it live. On the left is the scenario we use throughout the four environment: quiet, traffic, wind, babble. 5 seconds of each, and mode condition plant is on, meaning every environment change also swap the acoustic paths. That's the hard dynamic test. We run our proposed configuration on this scenario just before recording. Here's the results. This is a bank calibration R config for Bayesian posterior. Our first run was IMM-Kalman with Python backend. It took 418 microseconds per sample. It's almost 8 times of real time. It has overall 23 decibel of noise reduction, and the second run was an LMS with Python backend. It's way faster, but it has less noise reduction. We can see here the methods noise reduction rates. Third one was, it's loading, I think. Yeah. Third one was the same calibration like the first one. We can see here 5 seconds of each, and 200 window, and filter length is 64, but its real-time factor is less than 1, so it's almost running real-time. Actually, it's better than real-time. And these were the synthetic scenarios. I have uploaded, you can see here, you can upload a real scenario from here. I upload the real cafeteria sound, background sound, and here's the results. And below that, we have the time domain. We can see for this run, it's the original noise, and we see the suppressed sounds from here. Also the for the others. See, on the spectrogram, we see brighter points like low frequencies, after the IMM-Kalman, it's darker now. On here, we can see the noise reduction over time. We have the mean over here. Here the mod posteriors, like yeah. Let's look at this one. I uploaded the Babel audio, and we can see the Babel is the orange one. It's on the top. It's between traffic and Babel, but always selecting the Babel. We can see on the low frequency bands, noise reduction is good, but when the frequency goes higher, noise reduction goes lower. And on the last tab, we can compare these for run between each other. Let's run one quick. Yeah, mod conditions. It's the quickest one. Let's set like that and see. See, it's the single Kalman filter. We can see it works some region, but when the environment change, it can't adapt. And you can also hear the original noise. Yeah, we can see it fails on the after the 10 seconds. Now my friend will hand over to the music and feel part to understand what it's actually doing on virtual headphone scenario.
Yeah, thank you. So the graphs are all good to see like how it cancels the noise, but obviously music is just with our ears. So I'll play you uh, each clip. First of all, open ear, then with earbuds on, then with ANC on, and with NLMS and ANC. So then I'm gonna show you the music part and how it affects the music. Then we'll talk about the conclusions of it. So first, I'll play you the open ear with no earbuds. This is pure noise. And now with passive seal only, and it simulates basically what it feels to have an earbud on during the noise. The earbuds basically give like a good noise cancellation without the ANC, just physical constraints, but still it's not enough. So here is the IMM V5. And here is the NLMS. It's not far off, but IMM v5 basically outperforms them all, and it actually gives us a much smoother experience in terms of noise cancellation. But now with the music on. First, I'm going to show you the music cleanly, then with ANC on, sorry, no ANC, then with IMM, then with NLMS, and we'll discuss the conclusions. And here with the earbuds on, without the ANC, with noise. Yeah, the noise is very obvious in this part without the ANC. And now with the IMM. A much, much smoother experience. And now with the NLMS. The graphs told this to us, but still, when you hear it, you can hear the differences and what we do in practice much, much more clearly. So, to sum things up, single setting filters for short changes. The IMM for Kalman filters blended by a Bayesian posterior delivers 16 decibels across changing environments, runs real time in C, and we measure its limits honestly, down to the musical noise artifacts you just heard. Thank you for watching.